Yeah, g'day and welcome back to my channel. I really like lathes, so I've been working on modernising this beautiful old Schaublin 125 to Linux CNC. Now one thing I definitely want to do this week is finally plug this motor and gearbox assembly back into the hole which it came out of. And other than cleaning up my bench so I can actually work on it, it's about time this plate gets painted. Right, before we install this, let's take a closer look at this drivetrain. It starts here with a three-phase motor, and this is 3 kilowatts. Now this motor is a so-called Darlander motor, which means that its windings are brought out and you can externally switch them either for 4 poles or 8 poles, and therefore either 1500 or 750 RPM. Coming around the other side, the motor drives this pulley, in German a variator. In English I think we'd probably call it a constant velocity transmission. This bottom pulley can be pressed together, forcing the belt to ride higher up on the now narrower sheaths, which will then pull the belt on the upper sheath in, because this is spring loaded, so these will then spread apart and change the gear ratio. At the moment we're in the lowest possible ratio. Using this motor to adjust through this set of levers to push these sheaves together, you can reduce the amount of reduction and probably even reverse it so that that's turning this one at a higher speed than this one. Now you might be thinking that's a pretty darn complicated solution. Why did Schaublin go to all of this effort to put in all these mechanical components and a second three-phase motor just to change the output speed of the motor driving? And it's a fair question, but you do have to remember that in the mid-1970s when this lathe was being designed, the high power transistors necessary to make something like a variable frequency drive as we know it today hadn't yet been invented. The only options available to them were either to go for a mechanical speed reduction. I mean, other manufacturers often just used number of gears. Other manufacturers like Monarch used a big AC motor to drive a DC generator and then drive a DC motor to actually run the lathe, which, you know, this is even more complicated. The modern solution is either a big motor running a belt to the spindle, or even the spindle shaft having the motor rotor integrated into it. And basically just by having a massively overpowered motor, for example, machine this size, they might put a 15 kilowatt motor onto it and just run the thing through a VFD, variable speed, job's done. The actual range and speeds you can get out of this constant velocity belting system is really only from about maybe 2 to 1 to 1 to 2, a speed range of about 4 to 1. Because on a lathe like this, you're going to want speed range of maybe 50 RPM up to 300. You need a gearbox as well. So this gearbox has a back gear in it. It's either going to let the power come through and go straight out 1 to 1, no change in speed, or it drops from 6.5 to 1 to give you your low speeds. The final drive out of the gearbox up to the lathe spindle is just 1 to 1. You just need to take one look at this and realize that this was an expensive solution. Now, if you could avoid building and installing this gearbox, that's got to be advantageous. Actually, that gets me thinking, we need to talk a little bit about current development in large gas turbine engines. Let's start off by looking at 3 generations of engine. If we look back at the JT8, it had a 20-inch fan, and its fan turned at about nearly 9,000 RPM, and its core at about 12,000. You know, this was your old 737 engine. Going up to the A320, the CFM56, got a 68-inch fan, turned about 5,000 RPM, and about 15,000 on the core. Today, the LEAP on the A320neo has gone up to a 77-inch fan. It only turns under 4,000 RPM, and its core is up to 19,000. So as you can see, as the fans got bigger for more efficiency, tip speed limitations don't change. You're trying to avoid the excessive noise and shock drag with supersonic or highly supersonic tip speeds. As the fan diameter increased, you wanted fan speed to decrease. But the problem we got is that we need for the low pressure turbine to drive that fan. So as long as they're coupled together 1 to 1 on a single shaft, as the fan size increases and the fan speed decreases, then of course the low pressure turbine's RPM's decreasing, and the only way to get any real power out of it is to put more stages and increase its diameter. And we can see that if we look at the cutaways of those 3 engines, just how big those low pressure turbine modules became. So it's obvious that the solution is a big fan, but with a small, high RPM turbine driving it. And that is what Pratt has done with its 1000 series. So you've got the big fan, 81 inches on the Neo, but between it and the low pressure compressor is a gearbox, a planetary gearbox. While the low pressure turbine's turning at 10,000 RPM, the fan's got about a 1 to 3 reduction gearbox, slowing it down to a bit over 3,000. If that's so obvious, why hasn't anyone done it? Why is that so hard? If you think of the power going over that gearbox, that fan is probably absorbing somewhere in the region of 30 to 50,000 horsepower. Let's assume it's 99.8% efficient. If we're putting 50,000 horsepower over it, that would mean that gearbox is generating somewhere around 70 kilowatts or 100 horsepower of heat, which it needs to reject. One of the issues is you've got this major thermal mass here. Gas turbines are generally pretty skinny and light. You know, their frames and casings tend to be quite thin-walled, and therefore they don't have a lot of thermal mass. Once you put a big gearbox in there, you've got a thermal mass which is probably going to have to warm up before it goes flying. And another thing, if you look at where it's located, between the fan and the low-pressure compressor, there's no way you're going to get in there and do any real maintenance on this. So what's Pratt & Whitney competing against? Well, if you think of the average CFM56 currently in use on a 737 or an A320, they're probably somewhere in the range of 40 to 50,000 engines built, billions of flight hours, completely sorted design. So if you were to buy a brand new plane with a CFM56 on it, you can pretty much expect that if you've got a fleet of these things, 85% of these engines are going to run to their cyclic limit, which is roughly 28,000 cycles, with basically no maintenance. Just change the oil. Now, if you think of a typical like Southwest, EasyJet, low-cost carrier sort of style operation, they're probably doing 2,000 to 3,000 cycles a year. So you can pretty much plan on having no significant engine maintenance for the first 10 years of the aircraft's life. This is the big challenge Pratt is up against here, because Pratt's gearbox, although I've heard it's actually an MTU design, Pratt's gearbox is competing against no gearbox. There's nothing more reliable than the part you didn't install. Yes, Pratt's engine has got a way smaller core, should be significantly more fuel efficient, but the LEAP has pretty much the same fuel efficiency. If they can get the LEAP to similar reliability as the CFM56s, then Pratt's going to have a hell of a time if this gearbox doesn't last 10 years on wing without maintenance. And that's the big challenge for them. Hope it works out for them. Not an ideal to paint anything because it's bloody cold at the moment, but oh well. Once I've got it painted and the paint's dried a bit, I'll put it in my furnace room. There's really no point trying to paint directly onto this hot rolled steel because it's got a layer of mill scale on it. So I'll just give it a quick clean down. Try and get any fat or oils off it. But then I still have to remove the mill scale before I can start painting. So that bag's going to be big enough. I need to make up a little swimming pool for this thing to swim in vinegar. Right, there's that little swimming pool made. I'll probably need more vinegar than this. Only got 1 litre at the moment.
The next day.
So here we are after 24 hours. Now, you might look at this and go, man, that was stupid. All you've done is rust your sheet. But if you have a look, on the one hand, mill scale is just rust, but it's one of the oxides of steel that grips the steel much more strongly and is hard to remove. Whereas now, you can pretty much just rub it off with your finger. This red rust which formed also just rubs straight off. So that's the cool thing about using an acid to take off mill scale. You convert it from one of the iron oxides which grips tightly to an iron oxide which doesn't. If I had more vinegar, I would have just put it up on a couple of spaces to get the vinegar underneath as well. I now have bought a little more. Another 24 hours in there and it'll be ready for cleaning down, washing down, neutralizing, and then undercoating. Now don't shoot me, electrical engineers, but to simplify, A three-phase motor is roughly a constant torque device. So in a modern machine, you work out how much torque you want at the spindle and then simply put in a motor big enough to provide that torque. Here, of course, we can run the motor at a constant speed and therefore a constant power, and as we reduce the RPM through the drivetrain system, we're going to get a multiplication of the torque. So I think we should probably have a look and calculate what are the ranges of torque that you actually see in this machine. So here's our motor with our two speeds. We start off in the high speed. Through the variator, we can then either increase the RPM up to 3000 and go through the back gear in the 1-to-1 setting, and we get 3000 out at our spindle. Slow down the variator to its slowest speed, staying 1-to-1 through the back gear, and come out at about 600. So that's that first speed range. The second speed range is with the motor on its low speed windings, going out through the variator at its highest speed, no back gear, you come out at 1500 RPM. Slow motor, slowest variator, no back gear, you're out at about 300. So you can see we're getting these overlapping speed ranges. The next speed range is having the 4-pole high-speed motor and the back gear engaged. And the final one is, of course, the low-speed motor and the back gear engaged, gives you the final speed range of about 48 through to 230. Now, what's really interesting is because you've got the motor running at constant torque and you're using mechanical leverage to either increase or decrease the speed, 1500 RPM on a 3 kilowatt motor works out at about 19.1 Newton meters. So if you have that going up to the top speed, you end up at about 9.5 Newton meters. But what's really interesting is once you take that torque down through the mechanical advantage of the variator and the mechanical advantage of our back gear, you're up near 600 Newton meters of torque at the spindle. Now obviously there's going to be some frictional losses and stuff. It won't be quite that high, but you're probably still in the range of 550 or so. What a beast. I've already decided that I'm not going to implement the Darlander windings in this motor. Now in the original Schaublin wiring, you needed 5 of these massive contactors to run the motor forward and back, high speed and low speed. And the control solenoid needs 48 volt AC. But I decided rather than a transformer plus 5 of these big contactors, I'd just use a VFD. It's not substantially bigger than just 2 or 3 of these contactors plus their wiring. Now VFDs do come with one major disadvantage, and that is the way they chop up 3-phase power and put it back together again causes voltage spikes. So they need insulation class F on the wind. Oh, woohoo, that looks good. I just found this while editing, so let's go back and clean the mirror and have a better look at it. So does that say F? I sure hope so. Okay, so it is insulation class F. That really surprised me. And now I have to redo half of my video because I assumed it wouldn't be, and therefore I assumed the VFD would kill it. May still do so. I mean, it's a 40-year-old motor. The insulation may not be that great anyway, but at least there's a chance that it'll survive use with the VFD. And that makes everything a lot simpler. I can just go ahead, install this whole unit, keep the belt, keep the variator. I've got all of the control components for the variator, and I'll be able to integrate that into Linux CNC. The question is how I do the spindle speed control with VFD plus variator plus back gear, but that's just a software problem, which probably can't solve at all. Hey Sergey, you want to program something? But I assume it is going to die sooner or later. Basically, I'm hoping that it'll run long enough to get the machine running, and maybe even long enough to make its own set of pulleys to replace the variator. Then I'll put in a modern standard 3-phase motor and probably a poly-V drive. It'd need to run it from about 10 Hertz up to about 100 Hertz, so a 10-to-1 speed range, which is quite a bit. I'd probably need to add a cooling fan on the back of the motor to run it safely at 10 Hertz. A 4-pole motor should be able to run fine at 100 Hertz without any problems with its bearings. At 100 Hertz, you've basically halved the motor's torque, so the 19.1 Newton meters drops to the 9.5. That ends up pretty much the same as it was. However, at 10 Hertz, you end up, without that torque multiplying effect which you had with the variator, you end up with only about 125 Newton meters of torque at the low end. as opposed to nearly 600 with the variator. Is that going to be a problem for me? Never had any issues with lack of torque at low RPM on the Bolly, and that's only a 1.1 kilowatt motor. So what would you guys do? I mean, on one hand it would be simpler, I guess, to just throw out that motor now, get a 3-phase standard off-the-shelf motor, poly V pulleys, and make up a new belt reduction up to the gearbox. But against that, this motor owes me nothing. All the pulleys and everything are already in place. I don't need to muck around. I can just get the thing going like this, with the risk that maybe it dies immediately. I'm kind of hoping that I get a little bit of use out of it before it dies. What would you do? Replace or not replace? Plenty of other expenses in my life, and I don't particularly want to go out buying an extra motor for this machine. This is the powder for the dishwasher. It's probably got a fair bit of sodium hydroxide in it. So I'll make an alkaline solution to neutralize the vinegar once I've washed it down. Right, how's this look? Now the mill scale basically just falls straight off. Yeah, up here looks like it's dried out, so I've rubbed this down. But unfortunately, in some areas, I let the vinegar dry on the surface. And where that happened, I now have pitting corrosion. Oh well, I guess I now know which side's going to be the back side that you won't see. Right, I've already got a bucket on the floor, which has got some old plaster in it. So this vinegar and rust can go in there. That'll go to the recycling. You can see it's already starting to rust again anywhere where it dries out. Just give it a final rub down. One more rinse, dry it off, and get some undercoat on here as fast as possible. Still, if I'd used just a little bit more vinegar and kept it wet, you can see how nicely the rest of the mill scale comes off. No work whatsoever. Get nice blank steel. Right, I hope I've got enough paint, at least undercoat. Calibrated splash of thinners. I've just got to get these pipes run, the replacement tubing. Since this new tubing's much thinner, it looks like I'm going to need to 3D print some sort of a sleeve to go over here. So it'll still get clamped here, get enough length in it to avoid touching this, this rotating member. Oh, well, that looks nice and neat. Finally, I can start looking at putting the motor back in. Just had to jack up the front to get over the mounting boss. Oh, that was too much. Just need to lift up and get those steel blocks out. So there we have it, heathers and gentlemen, motor's back in, and I need to go and get this video edited. Thanks a lot for watching, see you next time.